So hi, today the main topic is, it's not really kind of main topic. I'm just gonna trying to do some interesting stuff, live coding, with some kind of virtual interview. Actually, I don't have really much that interview. Even for live coding, I only have two of it. But since though, I can still try the interview. So let's say live coding, but the main topic is the thing I have to make is the Btree. So I have to make Btree using JavaScript, but I'm just gonna practice. Seems like I'm using seems like I'm getting interviewed. Um, First thing I think to implement the Btree, I have to think about um, the um, the properties of what Btree has. Example, Btree. If you look at the Btree characteristic, Btree is not just the binary tree. It's not binary tree. There, the goal of the Btree is to make sure that the children has consistent pairs. Which also means that sorry about English. Which also means that the B tree, the children number has to be same. Has to be same with the others, with the other sub tree. And also the B tree, the main operations. Um, I'm just gonna increase this more. Yeah, the Btree main operations are insertion. First is a search, and insertion and deletion. Um, so let's try to begin with the abstract making the search first. First, I think I have just to make the page class. The reason why I use class is because it's to make it because this is not also OOP, but at the first beginning, I think class syntax is really kind of nice for the implementing Btree because um, it's really kind of easy to look at the which properties are have some kind of method. Example, in the page, so I mean the page means that the node of it. So page, but let's just say node. Since node can have the keys and the children. So children is gonna be the it is the multiple items or the node. So I think this I think to explain with the code, the keys are gonna be like this, and children we're gonna be like this. So constructor. Um, Now we have to make we have since node is the just is the inside of the B tree, and I think um, uh, it will have to receive the keys of it. So the keys, so it keys the children. So the this that keys we're gonna be receive the children keys, and the children will receive the children. Um, and also um, our goal, yeah, since there's no minimum degree that you I receive, so let's say the minimum degree is x3. So the formula to get no let's say 2. So the formula to get the max keys that node can handle is 2 times 2 plus 1 minus 1, which is the 3. So the max keys that can have is 3, and the minimum keys that can have is the minimum degree, so equals to the 1. So the node can have a max key which is 3 and minimum degree which is 1. So the best thing is this receiving minimum degree and manipulate those kind of logic inside the node method. So I think get max keys, that max key value, the max key, let's say length of it. Yeah, max key length. I think max key length, the method name is much better because right now we just define key as an array, so the key length is gonna be the, so rather than saying out the value, I think the length is gonna be more appropriate. So we're just gonna receive minimum degree, so which is gonna be number. It's gonna be number. Yes, so minimum degree is got number, and the formula is 2 times 2 minus 1. I think 2 times minimum degree, and then minus 1 is gonna be the original is the 3. But however, this formula looks kind of bad. How can I turn on the print here? Never mind. So since this code is kind of really hard to read, I think it's better to write as a function here. And return 2 times t equals the number. So t is gonna be number. So put t and put here and minus 1. So I think it's better to put in the here. It's like the functional programming. The reason why I kind of prefer functional program for this is because this is actually the thing doesn't change, because that's the formula. Since this formula doesn't change, it's just a theory thing and it doesn't change. I think putting as a code is a functional programming, and wrapping inside like this is gonna be more better to read, I think. So the pattern is gonna be number. So return is gonna be number. Yes, and so now I think this was the max key length, and now our minimum degree. To get minimum degree, I think I just can make method like this, like seems like get max key length. Or so I'm just gonna use functional program for this. So this is 2 minus 1. No, t minus 1. So formula is going to t minus 1. I just have to put it on like this. So this is kind of method that I just defined. And I prefer using static because this is actually the thing that is kind of inside the node of it. So I can just use it as a utils, but however, since this is have a more characteristic that this max key length belongs to the node, but you can just using from the utils, I rather putting at the static that I can use this function rather than opening the node constructor. So max keys length gonna be number. So I'm just gonna put it like this. Min keys length like this. So at the constructor, I were able to put into max key length and min key length value these object from using these static functions. Max key length. So this that node that get max key length get max key length get max key length and put in the minimum degree will be nice. So I will just able to get minimum degree on the constructor params. So I think this is the kind of really the the most basic thing to make a Btree. So next part, I think what I have to do is making a search query. No, I think making the tree first. So there, first of all, we just define which is node and what node can get. But I think most the important thing is the making the tree class. So there's a tree class. So inside tree class, we receive the node node class. So node is actually belongs to tree, because as we know, the Btree, inside Btree there's a like node there, and node is belongs to the Btree. So we're just gonna make the Btree class, and at the first beginning, here we get the minimum degree, and yes, I think here we get minimum degree, and this, I think this is pretty fine. Putting the minimum degree on the Btree class, that we can now know that which node can have a max keys or min keys. So I think it's better to define minimum degrees also in the Btree, in the inside Btree property. And also Btree, inside Btree there's gonna be multiple node, and the data, I think making I think is really kind of important to make some kind of data that holds the current state, which is the what node and what page it has. So this that this, I think, rather than putting here, I think this is gonna be really more better. Since when I tried to, so the reason why I put the node here is because at the beginning you don't really insert some kind of keys in the Btree, but still though we still have to initiate this kind of node to ready for the putting the key. So I put in the new node class object inside Btree property node. But however, since this new node requires this constructor, I just make it into assigning empty value that it doesn't store data. But minimum degree has to be minimum. I think minimum degree, since minimum degree has to be assigned from the outer space, and I think rather than putting it here, I think is better to put it onto a constructor when it reaches minimum degree. So let's just try to check if there's no errors or not. Let's say our minimum degree is the 2, and let's debug with dir, so that we can see how many objects. Node.index.js. Yeah, so if we can look at wait a minute. So new node, we just create a new node. I think page. Let's just use page instead of node. Page. Yes. I received 2. This received 2. So when I'm trying to receive 2, oh, the reason why it throws error because since the new page parameter only when it receives minimum degree, it doesn't know this minimum degree is belongs to the keys or whatever. So I think more better way is to put it like this. No, never mind. Putting it to like this, some kind of empty value. This page is not, oh, I didn't. So we now already define Btree. So I think the next step I'm just gonna do is get rid of unnecessary code, because we just self-assign the empty array, but we just trying to, when you're trying to receive this empty array, this code is it doesn't really work and necessary. So rather than let's just say self-assign, let's just leave the self-assign the code, but put like object mode that it doesn't. I think it's better to put the object mode that I can assign whatever I want, rather than rely on the position of the parameters. And children is gonna be like this part, and the minimum degree annotation can be used in the TypeScript. I think there's no annotation. Yeah. So now, since we don't have to really put empty array, because it just misleads the minimum degree as a case. So if I'm trying to use this using object parameters, I can just make a fully nice Btree object. Now what we're gonna I think first, I think it's better to make insertion, because we already made basic how Btree structure looks like. I think it's better to make insertion first, and then search and deletion, because the search has to be work after insertion. If there's no insertion and there's only empty value, the search is unnecessary. So I think the insertion would be better. Putting insertion on so I think it's better put the insertion method in the Btree. The reason why I put the insertion as a capital letter on the I is because this is public, and I think I'm sorry to keep on saying I think putting capital letter to inform that this Btree's method insertion is kind of the thing, is the kind of method that everyone can use. And the key is gonna be number. No, sorry, I think the key, the type is gonna be number, because if you look at the page constructor, the keys, we're able to get the number because we just defined the number first. And also most of the database, their ID is number, so I think it's really kind of better to think about the ID as a ID or key as a number, because we can just compare the value rather than rely on the string parsing. Key this dot node, so I think there should be insertion method in the node here. since Btree can Btree has to compare um, and sort these which keys can be inserted. Example, if there's like three, if there's like 3 4 5 4, the item has to be inserted. This should be arranged as a 3 4 5, because when when you receive 6, this page is full and we have to make this 4 as a primary key put into parents. So we're just gonna split into like this. So there's gonna be 4 here. And so to make it happen, this kind of logic that the sorting um, logic has to be done inside the insertion. So so making um, sorting logic is going to be more efficient and simple. And since this orange doesn't need to get the parameters because or object, because we can just reference this kind of this keys, because right now we perfectly know that our target key, we're just gonna focus on the current key. So this that keys that sort that A that B. So since to make it in that, and putting this orange function on the insertion could be more better. So we can just detect if there's any bugs on it. Example, if there's like something wrong with the arranging, I think we can just look up this code. But if there's something wrong without the arranging, we can just look at the insertion part of it, method of it. Arrange. So this that node that this the keys. So first we have to insert the key first, and now we have to call the orange function that makes sure this key is orange. And this insertion has to receive the key, and let's just run it like this. Btree and insert Btree that insertion, let's say 3 first. Let's just put the 3, and I think I'm pretty sure it's gonna work. Oh, why is there undefined support const Btree equals to new Btree to that insert 2 undefined. Oh yeah, the reason why it was undefined because I didn't return any values here, and after performing insertion, I can just look up how the Btree the property has changed. Now, it is kind of I'm pretty sure that the key is already inserted in the page here, since the Btree has a node which is page, and it has keys which is 2 because we just inserted 2. So the performance looks great. So let's insert more. 3 4. And this code, if it's orange is 2 4 5, and which also means that the orange logic is working pretty fine. And so let's run it. Since orange logic is working pretty fine, our next step, I think the next step has to be inserting the 6 or whatever 1 or whatever value to check if the node is full or not. let's just put 8 here. Yes, but the problem is that since our max keys is 3, but this leads into page full, page overflows. So to solve this issue, I think I will make to check that if current page is overflow or not, and is page overflows. This that keys that length is bigger than max key length. And now if you're trying to run it, oh yeah, I didn't put this on here. So if I'm trying to run it, it will say this code is overflowed because I just inserted. Oh, wait a minute, max key length CRG. Oh, I didn't put this on here. So since this page is overflows, is because the current case is really full. So if we detect this page overflow, I think I will just check if this case is actually overflows, and let's run it. I think there's something wrong with the code. Oh yeah. Wait. Sergi, this. Sergi, wait, hold on. I think there's something wrong with the detecting is page overflows code. Well, I didn't run a function, so if I try to run a function, it will working pretty fine. Yes. Overflows. Since yeah, this is working pretty fine. The reason why it doesn't work because I didn't run a function. So if after running a function and it validates is this function is this case is overflows or not. And since the Btree characteristics is that if there's overflows, select the primary key and put into the parent, and if there's like siblings there, push it down in the child. And the other issue, another method I think I'm gonna make before implementing this, selecting the child and push it and make them go to the child, is I think the making method of get primary index will be much pretty fine. Since the get primary index, there's no big formula of it. It's actually that minimum degree minus 1. So since we did not make the object for the minimum degree, I think putting minimum degree as a object property inside class will be much better to read or better to perform this. So I will make other code for the putting minimum degree as a property. So now we just now able to get the current primary index, and now we make sure that if the page overflows, we select is page if there's something wrong with the current keys on it, and we will perform selecting the for and pushing the parent. To make this happen, I think we will just have to deep copy the current page of here, because we have to copy it. We have to copy 2458, and we have to make new one, which is empty, and we have to put 4. And I think next time, and we have to delete the other siblings and make into like this. So the first is select the primary key. Second is make parent key. Third, split into left by child. Fourth is merge with parent keys. So let's just begin with the first one. Just select the primary key. Primary key is gonna be we just define as the method here. So const primary key primary index gonna be this that page primary index. And now const parent, that we're just gonna put the new node on. So the reason why we just make new node, because this parent also have to this parent, we're working on this part, so we have to make parent keys equals to we have to make our the parent page. So to make parent page, we can just put minimum degree as our current minimum degree, because it has to be this has to be the same minimum degree value. And now this parent has no any keys on its children. Now next, make the parent keys. Since this parent key have no keys, we just know which one is the parent, which one is the key has to be inserted. So our aim is, since this is our 2458, our primary index is 4, because 2 minus 1, our minimum degree was the 2, minus 1 is equal to the primary key index. So we have to make this 4 into primary key, which is the parent. So we make the parent dummy parent page. So page that since parent, the insertion with the this that keys that primary index would be more better. Now we just make the parent key with fancy keys, but rather than putting the insertion part, I would say just making as a fully built keys will be much more better than performing the insertion method in the parent. So that's gonna be more predefined, and that's gonna be really better to understand. Now we just make the parent, and next thing is split into left or right child. Since in the JavaScript we can split in an array, which is splice or split. This const dump splitted children. So this dot kids split. Starting point is at the first part, we have to only make the 2 as a left key. Now we have to splice 0 and the primary key index, the starting number, and delete count is actually 1. Wait, I think starting count. I think split will be much slice. Yeah, I think slice is much better. Starting from the 0 index and the between the 4, which is primary index, and this leads into, I think, the to only the array that has 2 key. So let's just debug it. And now as you can see, the splitting, we just split the child, and I just anticipate the first split the child, left child will be 2, and it printed really well. So the split it left const split it right. So this is the keys, the slice, primary index, and putting parent the current keys. This that keys that length will be much more will be slice this right child of it. Let's debug more of it. Yes, so the reason why there's a 4 printing, because I just misput the primary index on the slicing the right child, and if I +1 with the primary index, it was just gonna print out a 5/8. Yes. So the best option is to abstract this kind of functions into some kind of logic, that a method that get the which one is split on left right. But I think that would be more perfect, but right now we don't have much time, so I think it's better to put this on the to do has tab to abstract the split operation method. Now, so we just make the split left and split right, and let's just check if we modify this the case. I think the sliced one modify the original case, right? Yeah, it just returned a copy. And the best option is since parent there's no children, we can just define as children as a primary index here. Primary index, is this right? No. So since there's inside the children, the left part is going to be here, has to be here. So left, and split right has to be right of the array. And if we're trying to debug the parent the children, so as you can see, there's a split left and a split right. We just make the split left and split right, and since is already fully made key, we have to put in the children. However, this has to be the page of it, because children can only have the page, only page children, but we just put it into array. So right now I have to fix it into making this as a page object. So rather than splitting the left key, so this is actually keys part, left keys. I'm just gonna perform new left page, new page. Of course, you will receive the minimum degree. And the key is gonna be left keys. And the right is gonna be very simple. Right case. So right page is really kind of same as a left page, because what we have to do is assign the fully made case into new page here. So if you're trying to debug it, the left page keys is not defined. Oh yeah. If you're trying to debug it, so we now able to make the Btree that has the keys, 2 keys, and the right power to 5, 8, and now we have a parent which is 4. And now the best option is making override this parent logic, this parent on current keys. So this I think it does work. I think this is kind of very bad code, but yeah, it doesn't work. Since the problem of current code is, I think I didn't it breaks the rule of immutability, because there's a bunch of code that construct a new page and there's no private method, and I didn't anticipate private method because I'm using plain JavaScript. So we make the parent page, but we also have to put into current object, and the best way is overriding. I think I can just make it like this dot keys equals the parent dot keys, and this dot children equals the parent dot children. And if I try to run it with the console log, the Btree part, yes, so the main problem was it breaks the rule of immutability. It was the current property, but we are just overriding that. We just have made a parent that the parent has to be delete the original code, original object, and it has to be changed. But I think this code is not really fully great. I think there could be on the object, but since our goal is to make the Btree first, I'll just keep this code. So next, I just already made the insertion part, and let's test it more. Since we trying to insert 2, 4, 5, 4, 4 to 5 to 5, 4, 8, 9, 1, 0, 0.4. If I turn to orange, it was gonna be 0.4, but whatever. But wait, if you're trying to arrange it first, 2, 4, 5, 8, 9. But let's just skip first this part first. 2, 4, 5, 8, 9. The 4 is gonna be primary key. It goes to parent. The 5, 8 gonna be 5, 8 go to the right. But since 9 is also the right, the bigger than the 4, we have to put in the right. And next thing is 1. 1 is smaller than the 4 and smaller than 2. It goes to have to next to the 1. And if it's 0.4, it has to next also for left part of the 1. So it has to make as a like this kind of Btree, and let's just try to perform that. The reason didn't work is because I think wait, hold on a minute. It doesn't work. Oh yeah, the reason it didn't work is because um we just post um we just put the key on the root of the page. The bit tree is actually the extent of the binary tree. We have to make sure that our insertion has to be on the leaf of the page, which also means that if there it has to be inserted on the most bottom of the bit tree. So I'm just gonna make is leaf returned this that children length equals to 0. If it's leaf the children, there's no children, it has to be inserted. But now I think also I have to make some kind of method that it leads the direction. Example, like we just look, if 0.4 is smaller than the 4, it has to go to left. But those kind of like putting left or right index, getting index has to be making it as a method, so we can just debug it. We can just debug, or we can just capitalize more better to for the potential bug. Get next child index, really nice. You're just gonna receive the target key, which is number, and I will just check if there's any index of it in the current keys. So keep that keys, find index, find indexed. I think find index more better. Find index, which is key smaller than the, I think core key is gonna be more better to read. So I think sorry keeps on talking about I think this could so the reason I put some kind of find index logic is because, example, our target key to insert is 5. Since 5 is not smaller than 2, it has to go to the right. Since let's say 4, the 4 is small, it's not really smaller than 2 or bigger than 5, it has to go to the inside of the current node. So I think best way is to compare the 0 index value and the last index value, and check if there's more children's. So get child index means that there should be children there should be children. So the get child index is gonna be the first priority is has to have children, and next, if there's a children, we have to compare the which direction, some left or right. Yeah, so if this is left, if it's left, we can just push it. So the next direction is gonna be no, I think the insertion logic is gonna be like this. So this one is kind of wide range of inserts that the page overflow, those kind of logic, but I think this is core insertion logic that if it's left, we just now put into our current keys and now arrange it. But if there's no leaf, we now have to find which one has to be traversed. For example, the next index gonna be next chart is the index gonna be it's gonna be if her key is smaller than keys that 0 is gonna be 0 and wait, hold on, 0, 4, 5, 6, 7. Yeah, you better to use the index of it. Next chart index, this that keys that index, find index key. So query key is gonna be smaller than or than keys number 0. Next key is gonna be next one is traverse is this key this that keys this that children that next that child index. Yeah, so else return. Yeah, I think it's gonna be more better. So the main problem was we just make insertion logic on the root of it. That's not the Btree. We have to find which one is index, which one is children or not. I'm just trying to just get rid of this kind of method because it just making me confused more. So if it's live, push it and arrange it. But if it's not live, we have to find it which part has to be done, and this children has to traverse more. So those logic is unnecessary. Where did this come from? Yeah, this is unnecessary. But after performing the children, so this page overflow logic has to be inside the is live logic. So like this part. And now this putting the next children, if it's live, it says no, we have to perform the next children and traverse more again. So next children, that insertion, the key. So we're just gonna run again. Nope, curly key is not defined. Just push the key. Oh yeah, we're just gonna make it as like this. Curly key. Yes, now we already performed the 4 to 5. There's no 9 over here. It's very strange. We have to perform 9. We just debug with the 9 because it has to be work. CG, current key is current key and next children. So if current key equals to 9, we just debug this next child index is correct or not. So -1. So the reason why it throws some kind of error is because so we didn't put some kind of validation that there's no matched results. So safe in child index gonna be if next child index equals to 1, it means that it's really bigger than the other current keys, so it's just gonna be that keys, that length, else it's just next child keys. So let's just, and now we have to put a key in here. Now, yeah, so our goal is to perform the Btree insertion, and the top has to be 4, and next left will be left, 2 it has to be go left, and 5, 8, 9 should be go right, and it perform really well, right? So if I try to delete this annotation and run this code, it has to be performed. The left part would be 0.4 and 1 and 2, and the right part it has to be 5, 8, 9, and the parent has to be 4. So let's debug it. Yes, so it's working pretty fine. We now able to get the parent, which is 4, and left part is 0.4 and 1, 2, and right part is 5 and 8 and 9. Now, so we just make minimum insertion, but I know there's more, because if there's like propagation of split, because if I try to add more of it, there's gonna be page overflows, and I have to make parents of it. If there's more parents, I have to merge with the current parent and the previous parent. But since this is kind of there's no time for it, I think making search operation would be more better than putting some insertion logic, because I already implemented insertion logic, and there's no rules of how to implement implementation insertion. There's no limitation of it, so I'm just putting into most simplest insertion page logic in here. Now it's a search. In the search, I think it's really kind of easy. Search if I can just get this kind of logic here, the getting safe index value. Copy paste it. If query key found, so using that keys that find key. So right now what I'm doing is I'm just checking this current keys have our core key. If core key is found, we don't have to really go to other logic, and we can just return the true. But however, if there's no true, we can just we now have to traverse more, and this is save child index to traverse. But this is only valid that if there's more children, and I'm just gonna check is live. This is live equals to true. That means the reader's query found here. There's no query found, and if it's already live, we just now say that there's no other query keys in this Btree. If there's no, I just have to traverse more that I just have to traverse more. So let's run it. Since we now able to put this fully made Btree, and if I try to run this search on the 2 or 0.4, it has to print in the true. And let's search. Let's perform the search. If I try to put the 0.4, it has to be printing as a true. 1, 2, 3, let's go. No, it's code undefined. Why? I didn't return it. Um, 0.4. It gets the number. The reason why there's undefined is because I didn't return it. If I return it, this is gonna be true. Yeah, so this is printing true. Let me just try to delete other console log here. Where's other console log? I think there's no more. So we insert the 0.4, and now we search it, there's 0.4. And let's go deep more. Let's just say 9. Yes, there's already we can just now 9 as we fully searched 9. So let's try to say 4. Or just print it true. And let's say, what if we put the 2000? We didn't add any 2000 key on the Btree, so it will print it as the false. Yes. So now this is kind of the end of live coding, like getting interviewed by how to implement the Btree logic, the insertion and search. Of course, there's a deletion. Deletion part is really more difficult, and I didn't implement the full insertion logic because my back hurts, and I have to sleep. So I think this is it. And I don't have really much of getting interviewed with this language. I'm a native Korean so I don't know what I'm doing right now. So what I'm doing good or not. So this is it. Have a nice day. See you next time. Bye bye.